Morning, everyone. I hope you all had a lovely weekend. Relatively warm, no snow.
Good morning, Professor.
Good morning. Just in case any of you are interested, have a little free time, that movie Hidden Figures is running on HBO, the regular HBO, not even the streaming too, but I mean it's actually just running on the channels. So it was funny because I was flipping through the channels and I saw it and I said, "Ooh, I'll put that on later." And my son was like, "Oh, put it on. That's like one of my favorite movies." And I was like, "Wow!" Like really surprised me that he would put that in because when it came out, we had a bargain. I had to go to Star Wars if he would go to Hidden Figures, and he loved it. Um, so again, I recommend it. It puts a historical context on a lot of stuff. I mean, even just the whole process of how computer science became such a part of our lives. And it was no part of anybody's life in the 60s, including scientists. So anyway, all right, a couple of announcements before I start today's stuff, because today we're going to work on sorting algorithms. Um, your project is up. It was visible. This morning it wasn't visible. I reloaded it. Um, the specs themselves of what I want you to submit will get a little bit more specific over this weekend because I played with what I wanted you to do. But as you can see right here, the idea of the program is we're trying to get an analysis of sorting algorithms. Okay. I said to you, I don't care that much about the sorting algorithm code that's readily available for all of them. Okay. Um, and what I'm going to recommend, the way I think you should start this whole thing off, is look up clocks and stuff. But first of all, just write a program that'll generate an array of 10,000 random integers between 1 and 100,000. I mean, if you want to do 1 to a million, go one. It doesn't really matter. But it's a large array. Okay. I want you to sort the array using insertion sort. Now, I'm picking that because insertion sort is probably the best of the n squared algorithms. It's a comparison sort. So it's a legitimate thing to add in with all these other comparison sorts. It is an n squared algorithm, but in many instances, it's actually faster than the n log n's. Because we'll talk about it today, we'll look at the code. It does a minimal amount of moving. It does more than some of the other algorithms do, but it's also straight array notation. There's no recursion involved, there's no pointers involved. It's a straight array implementation, and it's a fixed size, so an array is a good thing to be able to use. Um, so you're going to run the insertion sort algorithm on an array. And make sure you save the original array, because then I want you to pick at least two of the following. Heap sort, um, oh, I want that modified heap sort out of there. I want that to be merge sort. I'm sorry. Like I said, I was playing with this thing. Um, I'll reload this. merge sort, and quick sort. And with quick sort, I want you to run that both ways. So the modified version, but start with the basic edition. And that's the way we'll define it today, and then we'll talk about the modifications. Now I know you know all these algorithms from 313. So like I said, I don't really care if you use the code from 313, if you use some other code of your own. I'm going to write some pseudocode today if you want to play around with that. Just make sure that you store the original random array because it's going to mess everything up if you keep once you sort it. If you sort it and then start running it constantly on the sorted arrays, it's not going to be a valid comparison. Run it one time. Make sure everything is working right. Okay, you don't have to print out, first of all, don't print out all this stuff, okay? Um, if you want to make sure it's working all right, do a test with just 10 integers or, 20 integers. And then, or what I did myself when I've run this is I had it print like the first 10 and the last 10 elements of the array when it was done. Assuming the 10 smallest and the 10 largest show up in the right place, I'm going to figure out the rest is okay. All right, so that's what I would start with. Just do that much to start. Once you have that working correctly, and you'll be saying, oh, I'm not getting in any trouble with that. You will. Once you have that running, then I want you to add in something to keep track of the exact clock time. Okay, so not the generating the random array and stuff like that. But once the actual sorting algorithm begins, I want the actual clock time. Um, and building an accumulator so that when you run this many times, you can find an average clock time. I don't want to see a listing of 1,000 runs of sorting algorithms and their times. I want to see the minimum one, the maximum one, and the average. Because right now, everything we're talking about, we're using this asymptotic notation. I want you to see how that really comes to play in the real world. And part of this is going to show you that insertion sort can be better on small enough arrays. Um, I want you to see the difference between n log n and n squared. I want you to see the difference between merge sort and quick sort, or merge sort and heap sort, or quick sort and heap sort. Two out of those three. If you want to do all three, fine. It'll make your program more interesting. It's not going to significantly increase the work. It'll just give us, more data to look at. Um, so I wanted to see an average runtime, the minimum runtime, the maximum runtime. Hold on, I got to move over my little window here. Now, I saw a message, and where did it go? No, any two of those three. So heap sort, merge sort, heap sort, quick sort, merge sort, quick sort. With the quick sort, I would like you to run it both ways. Only because, quick sort has a worst case. And I'd like you to see that, you're going to run this 1,000 times. You're probably not even going to hit a worst case. You're probably not going to hit an n squared. We're going to deliberately force an n squared at the end. just to see what happens with the n squared runtime. Um, you have to do the insertion sort. Okay, so the insertion sort is a must because part of our analysis is going to be, you know what? With 64 elements, insertion sort was better. Now, does that mean if my original array is more than 64, do the others if it's less? No, it means if I'm doing something divide and conquer, and think of how divide and conquer, what do I mean by divide and conquer? Anyone want to explain that? First of all, you know what? Let me do a real quickie poll. Do you basically remember quick sort and heap sort? I'm not saying you could write the code, but do you remember the idea behind them? Heap sort you may not have done, but everyone should have done merge and quick. Out of how many people are supposedly here? 32, only 22 have answered me. You know, by the way, I was marking the attendances down because I had to do the roster thing. And there are some of you that your total attendance has been like 10 minutes. You log in every day and then you log back out. Or you never answered any of the polls, which means you left your computer running, but you weren't paying attention because there's nothing in any of these polls that can hurt you by answering them. They're just yes, no answers, so I have an idea. All right, so it looks like most of you at least remember the idea of how these divide and conquer algorithms work. I mean, it's literally you split the array up and then sort the smaller arrays. The basic algorithm is written that you go all the way down to one element or two elements. When you're down to just one or two elements, you stop the recursion and you do the merging, or you do the partitioning when you get down to that. You stop the recursive calls. Um, but you may find that once you hit 256 elements or 16 elements, whatever, at some point, insertion sort is faster than the divide and conquer. So when you're dividing, when you hit that breaking point, so you get down to 250 elements, and now it's faster to do insertion sort. Fine, call insertion sort. Jump out of the recursive calls to merge or the recursive calls to quick. Heap sort, for those of you who don't remember. All right, let me do another quickie poll. Did you see heap sort? Okay, a chunk of you didn't see heap sort. Um, I'll go through heap sort too. Heap sort is not a divide and conquer. Heap sort is iterative. It's a straight for loop, but it's an n log n runtime, and it's a good n log n. Um, and the main advantage is it's not recursive, so you don't have to worry about blowing a recursive stack for a very large array. You don't have to worry about sorted data causing a worst case. It's not going to. Um, it's not quite as fast as quicksort, and no one can really explain why through all the analysis, they do a lot of analysis on these things. And from all the analysis, quicksort should be faster, but it's More faster. I mean, it's faster than it should be. And it's really just because random data does kind of fall into best case behavior. Um, it doesn't trigger that many bad things. If the data's sorted, it's horrible. But so anyway, once you have this all running, you've got an idea of what your range values are, min and max. Then I want you to create a table. Now remember, every time you run it, you're going to get different results. It's random. So, you've got to make kind of broad categories for min and max. Um, I want you to create a frequency table. I don't want to see all 1,000 times, okay? But I want you to tell me that, 200 of them ran between 3 and 4 milliseconds. 50 of them ran in 1.2 milliseconds, or between 1 and 2. And 5 of them ran more than 8. Something like that. So we can get kind of a distribution table. And what I really want to do is when we have all of these run, um, so now you're really just collecting data. You're collecting data on runtime. You're going to collect the data on how many times you actually had to swap an element, how many times you did an if statement. Those are just going to be count statements. Count, count swaps plus plus. Count compares plus plus. I mean, it's simple. But put them in, where you need them so that we can get an idea of what data triggers what behavior. Do you see what I'm talking about? I'm trying to give you something very practical, something that helps you analyze data. It's a skill you will need in the workforce. And what better place to do it than with something you already know, at least something about? You know the theoretical runtimes. You know theoretically what's running best. Now let's see what actually runs best. What things other than the algorithm itself are going to affect these runtimes? Anyone have any ideas? What things might affect the runtimes of these different algorithms? The actual clock time, not whether it's n squared or n log n. What stuff would affect the actual clock time? Come on, you're like in your third or fourth year of CS. You should be starting to think this way. Yeah, the PC specs. If you've got a faster processor, or maybe your processor has more parallelism built into its data path. Um, what your operating system is, how efficiently is your operating system handling recursion? If it's doing a bad job, I don't want you using Python, okay? I don't. Because Python's going to muddy something in there. One of the big problems with Python, and I think I've mentioned it before, is it does not optimize recursion unless they've done something recently with it. It did not optimize recursion. And again, the attitude was if you're stupid enough to use bad recursion, go ahead and suffer with it. Python is not written for speed. It's written for ease of reusing code. Python has been developed to make it super easy to take a program you wrote for something entirely different and with a couple of modifications and a new set of data or a new plug and play data structure, it's good to go. Okay? But that doesn't mean it's going to be as efficient. Um, do any of you, this question used to have many more yeses than it does anymore. Do you know how to drive a car with the shift? Yeah, it's kind of sad. Honestly, I know in theory how to drive a car with the shift. Um, my father started to teach me on our old car right before he was getting rid of it because the battery was shot. The electrical system was shot, not just the battery. And I was like, but I want to know how to shift. I want to know how to do a manual transmission. And he said, okay, but as soon as you stall this out, we're done with the lesson. So I stalled it out a block from home, and that was that. Um, Race car drivers do not want to drive an automatic transmission. They want that control. They want to be able to control how things are being handled, um, how it's moving from one gear to another. Okay. Frankly, if you're ever going to rent a car in another country, learn how to drive a shift because they charge you way more to get a car with an automatic transmission. They're more efficient. They're more efficient on the gasoline. You have more control. My new car, the car I got last year, it's an automatic transmission, but it has an option. I can not pretend it's in manual. You can do that with any car. I can actually switch it into manual. I haven't. I had planned to play around with that when I was off over the summer, but I got sick and really haven't been driving much since then. So, it actually has it built in. I can put it into manual mode and then shift it myself. Of course, the shifting is weird because it's got a touchpad, not a regular stick anymore. My car's just got a touchpad kind of control, a joystick control for the transmission, the gears. But so anyway, your operating system is going to affect the runtime. Your hardware is going to affect the runtime. Your language is going to affect the runtime. C++, plus plus, you have more control than Java. And if we went ahead and made this all objects, we would see more changes. Okay, because right now we're doing integers. If I had you run even simple names, we would see a difference in the runtimes because now we have to use objects for everything. And once we're using objects and pointers, we're seeing those kind of changes. So these are all things that would affect it. And that's why I'm going to ask you in your final analysis to include the specs of your computer. The cache size, that's going to have an effect. What stuff you know about your processor, how many cores are there, what's running on there. Um, is it supporting parallelism without you writing this as a parallel? I don't want you fooling around with parallel algorithms. Um, what language did you use? What your operating system is. Is this running faster on OS than it is on PC stuff? Or if any of you were running Linux or anything, your own operating systems. Okay, and this is the kind of stuff we're going to do. My plan is to make a Google Doc. Oh, that's my favorite call. I got to silence this thing. It's early today. Usually they don't start till 11. Have you guys been hit like horribly with spam phone calls lately? I mean, everybody I know is complaining. It's constant. And they're, like Sunday morning, Christmas Day. Christmas Day, I got like 10 spam calls. It's really annoying. And there's no way you can really block it because they just use dummy numbers. And yeah, changing your phone number is just so annoying. Yeah, I'm getting people that want to buy my house. I'm getting told I've been approved for a loan. I didn't apply for a loan, and I know this is, that's phishing to get me to click on something. But anyway, so I just put this on. Wait, did I put it on vibrate? Just in case there's something I need to attend to. But I can't have the spam thing going off every couple of minutes. It's just too much. Okay. Um, I like that they're buying your apartment building. You've got really creative spam. Okay, so anyway, I'm gonna make a Google Doc eventually for this thing so everyone can enter their data, and then maybe we can have an extra credit thing where you can, run some stuff on the raw data, some of the variety of things that you might want to do. Anyway, does this all sound doable? In general, I've given something similar to this. I change what I'm looking for every time, but I've given this idea of running the sorting algorithms different ways in the past, and people seem to find it interesting because you've never really looked at the actual numbers before. You've heard n log n, you've heard n squared. You haven't really looked at, and I think it's surprising that these things run in milliseconds. And we're talking about, large arrays multiple times. And now nobody's talking to me. I got 14 people answering me. Are you afraid? If you're nervous about it, I suggest you start this weekend. Just get the beginning part running. Get the algorithms to work on an array of 10 elements, 20 elements. The magnitude of it is just because 10 elements or 20 elements is not enough to see what's, first of all, it's so fast you're not going to see it. Um, but it's not enough of a randomization. Okay, setting it over 100,000 numbers and picking 10,000 out of there. That should give us a, relatively random thing. Don't wait till the last minute. Now, I'm probably going to have to adjust this date just because whatever happened that it wasn't. Why isn't this moving? Why do I have weird numbers out in the... At 10 elements it is. At 10 elements, insertion sort is faster than the n-log ends because it's very direct. The difference, that will depend on your computer. The difference shows up traditionally, they've claimed 32. Some people had it showing up at 16. Some people had it showing up at 200. So it really depends on the specs of your computer, the operating system, and the language. At what point, Java optimized, although C++ optimizes recursion too. The framing. If you've taken 340, you know what I mean by that. If you haven't, don't worry about it. It's the language itself corrects some of the stuff. All right, so anyway, I think you'll find it interesting. It's not hard. You can't mess up the algorithm, the sorting algorithm. You can mess up putting in where the timers are or the randomization. Just look it up on anything if you don't remember. Just put it onto any search to get the clock. You can set it for, I think the basic setting is milliseconds. Nanoseconds you don't need. Seconds you're not going to see. Any of you been watching the Olympics? In particular, watching the racing part of the Olympics. None of you? Really? I got no sports nerds at all. All right, Keith. All right, now I got an important question, Keith. Mets or Yankees? Oh dear. Thank you, Sharon. Um, that's okay. Um, one of our other things is going to be a simulation of the Mets and Yankees in the World Series. Finding the probability that the Mets. What's the probability that the Mets will win the World Series against the Yankees? You can just put it in the chat. Oh, Sharon, you are a dreamer. Um, Unfortunately, Chris and Keith are probably right, but we came darn close in 2000. It went to the seventh game. I think it was the seventh game. I don't watch baseball anymore because I'm insane. I grew up with the Mets and 69 Mets, and I actually have a lot of memorabilia from the Mets between 67 and 75, including signatures and pictures with a lot of the 69 Mets. Um, but yeah, the probability is a lot closer to that zero than the 90. But we always hope, right? There's always hope. Every year there's hope. Anyway, that will actually be a simulation a program that we might run um, to get an idea and then match it to the theoretical probabilities. There's lots of fun things we can do in this class to illustrate what we're doing. All right, so now let me, um, any questions? Look it over. Don't jump to any conclusions one way or the other yet. I think you will find the code itself. Keith, the code itself was pretty easy, right? Just because, I mean, you actually ran it, so you've seen. Yeah, the code itself is easy. Um, and like you said, it was kind of confusing to you. You know heap sort is an n-log n algorithm. Why would it actually be faster to use insertion sort? So we're going to look at them now. I'm just going to switch the screen over. Hmm. Oh, it would probably help for me to actually reopen the Zoom. Oh, in case anybody thinks I was crazy putting up about class being closed, I had students complaining on Thursday because I didn't start class on time. Why isn't the Zoom link open? Because school is closed? Okay, I am maximizing the screen. There we go. Took long enough. Okay. So, our sorting algorithms. I'm going to start, and I hope I get through this okay. I'm counting on the fact that it's Wednesday, not Monday. I'm still on my first cup of coffee, so all right, this is an important theorem. Every comparison, now, comparison sort. Okay, so we're not talking about rated sort, count sort, those. Some of those, they run what's called a pseudo linear time. They're not linear time. They just have two metrics. Um, Two things that affect the runtime. One is the size of the array or the size of the data set, which is not a surprise. But the other can be the magnitude of the data, how big the numbers are, or the range of the data. And they actually will affect the runtime, the theoretical, the n log n type thing. So it will look like it's linear in terms of the size of the array. But the second piece of information, how many digits there are in the data or something like that, that's something separate. And it contributes to the runtime. So there are two different things. And basically you get into some kind of if the magnitude of the numbers is larger than log n, you're better off with the comparison sort because now it's going to be running slower. Okay, so we're talking about straight compares, things that are swapping data around. So we're going to start with a theorem. I want you to see, that there are proofs of this stuff. Some of you may have seen it in 313. If you had it with me during a regular semester, you probably did. If you had it with me in the 4 week summer, you probably didn't because it's intense if you're doing a, 3.5 hour class. We're going to start by considering We're going to start by looking at the tree that's generated by comparisons on a small set of data. I want you to see what happens. So say I just want to sort three elements by comparison. So let's say I'm going to start by just checking, is A less than B? I'm going to make these distinct elements. It's not going to hurt anything if they're not distinct, okay? It's not going to change anything. All right, so the way we're going to build this, look at this tree, is either A is less than B, yes, or it's not, no. If A is less than B, what would be the next question I would want to ask? You can put on your microphone to answer. I've got three random elements, three random numbers. If I know A is less than B, what would be the next question I'd want to know? Oh, come on. Okay, we could go either way. I'm going to go with B less than C. But you know what? You said go this way. Let's go this way. All right. So the next thing I want to know is A less than C? Again, it's either yes or it's no. Oops. If A is less than C, so now I know A is less than B and A is less than C. Anything else I need to know? So right now I know A is less than B, A is less than C. Is B less than C? If B is less than C, what can I say? Do I know what the order is now? Yeah, now I know it's A, B, C. If B is not less than C, do I know what the order is? ACB. All right, if A was not less than C, so let me come down this side now. So if A was not less than C, what's my next question going to be? So now I know A is less than B, Hopefully the colors will keep me straight here. A is less than B, but C is, ugh, C is less than A. That looks like two A's there. I'm sorry, I just made some weird, bizarre scribbling all over the chat. So I have A is less than B, C is less than A. Anyone? A is less than B, C is less than A. We already have the order. I know this is going to be C, A, B. This is really not working well today. I don't think you're seeing the bizarre stuff I'm getting. Because I've got the tablet resting on the laptop. Okay, what about coming to the other side over here? So let's now go looking at A is not less than B. So B is less than A. What do I want to ask now? Is C less than B? If C is less than B, what can I say? I have how many people? 34 people, and 33 of you are asleep. Come on. Yeah, I've got the order. I know it's C, B, A. If C is not less than B, that means I have B is less than A, B is less than C. What do I have to ask now? At this point, I know B is the minimum. Now I need to know, is A less than C? If A is less than C, BAC. Otherwise, oops, BCA. Now, do I know that I'm done? Do I know this worked? Do I know this is right? Or am I just hoping it's right? Because I don't want to make an idiot out of myself. And you know what? I could say it's right because I don't think you guys are even listening to me. How do I know it's right? What do you see there?
I think based
Look
on
at the
three
leaves of
elements,
the
there are
tree.
six possible.
I'm sorry, that was my fault.
The was my what I called six.
Yeah, you see all six permutations, right? We know there's 3 factorial ways of arranging those elements, or six, so I compared every element against every other element, and I see all six possible outcomes. So I'm going to make a note. Note, all n factorial permutations are represented. And the solutions are where on the tree? They're all on the leaves. Now, I know some of you in 220 spent a lot of time on trees and graphs. In 313, you did talk about the leaves of a tree. And does anyone remember how many nodes, total nodes there are on a tree with, or what we can say about the internal nodes of a tree and the external nodes of the tree? Anyone remember that?
Um, Professor, what do you mean by that question?
Okay, so let me do a little scribbling here. Okay. The internal nodes of this tree are the ones in purple. You know, get it off highlighter before you try to write. Look at how many purple nodes are on this tree. 5. And how many external nodes were on this tree? How many leaves are on this tree?
6.
6. This is always true. So the number of internal nodes is the number of external nodes minus 1. That's true for any tree, any binary tree. Which means the total number of nodes is equal to 2 times the number of leaves minus 1. But in this case, the number of leaves was n factorial. Okay, so far? Yeah, the internal leaves are parents. They're root nodes of each subtree. What would be the minimum number of levels or height of our tree? So if somebody went in the opposite, Keith, you went the opposite way. You went the number of nodes by the height, which is 2 to the n. So the number of levels or height by the nodes would be log n factorial. Yeah, I know. I've got a 2, so plus 1. I've got a minus 1, so they kind of cancel. So the sorting is going to be equal to the height of the tree. Since no matter how well I ask the questions, the number of comparisons is going to be how many times I ask the question, which is the trip from the root down to the correct sorting, which we know is the height of the tree, bounded by the height of the tree. I mean, we got out fast on a couple of them. We got out fast on ABC and CAB. No, we got out the way we asked. We got out fast on CAB and CBA. So therefore, the number of comparisons is less than or equal to the log of n factorial. We're almost there. Now, a lot of you looked this up for the homework. Oh, by the way, I don't know, for some reason I must not have published. I mustn't have hit the publish all. I thought I did. So they'll all be published today. I mean, you did well on that homework. I gave everyone a freebie. I gave you 2 freebies. The log of n whole thing factorial I gave you no matter what you put. And I think the 2 to the n factorial. Because some of you, I saw, I mean, your logic kind of made sense. You said it was a 2 to the n, it was 2 to a variable. But the n factorial is such an obnoxious exponent that it really was the worst of the ones up there. It's much worse than 10 to the n or 2 to the n. It doesn't fall into the regular exponential category. So, if you got others than those 2 wrong, you got 9 out of 10 or 8 out of 10. But in general, I think there may be 1 or 2 of you that I put a little note like you better go over limits or something. Um, oh, big announcement. Monday. Monday, we're going to have a multiple guests at the end of class, 10 minutes. Mainly because I want to make sure that we're okay working with a quiz on Brightspace. It's going to be little o, little omega, or theta. Give you two functions and you got to tell me, is it little o, little omega, theta? I'm not checking work on this one. I just want to make sure that the quiz is working right on Brightspace. I've never done a Brightspace multiple guess quiz remotely. I've done it in the classroom so that, when there were problems, I could immediately see what was going on. But I've got to make sure we can work with things remotely, okay? All right, so a lot of you already know by looking it up that log n factorial was what? And log n. Now I'm going to show you a really cool way to get that, okay? Okay, first of all, again, I'm going to note. Okay, since log n we know is theta of natural log, right? I'm not going to worry about the constant multiples that would change it from natural log to base 2. All right, it's either the base 2 log of e or the um, natural log of 2, whichever way you write it. It doesn't matter. I don't care. Okay, it's different by a constant multiple. We're living in theta world, so I'm not going to worry about that. Or actually, we're going to be living in big O world and big omega world, but okay. Log n is a monotone ascending function. Uh-oh, what class is this starting to sound like? When did you hear words like that last time? Let me make that increasing. Even more so. Oh, and this is again just yeah, calculus, exactly. This is how so many calculus proofs begin. Sometimes we have to assume with loss of generality, without loss of generality, that we can claim these, but this we know is true. Okay. So what does log of n factorial really mean? Well, it's log of n times n minus 1 times n minus 2 all the way down to 1, right? Which by rules of logarithms is log of n plus log of n minus 1 plus log of n minus 2 plus log of 1. Or the summation I equals 1 to n log of I. Okay? You with me so far? Big
Yes.
pool coming. You know what? Yeah, just react. Give me smiles or, I don't know, the looks of horror, whatever one is appropriate. I'm hoping they're mostly smiles or thumbs up. Ooh, got exploding happy stuff. Very good. Nobody's got the horror face up. All right. I'm with you guys. Okay, now here's some more calculus. I'm sorry. I can say the log of I from I equals 1 to n is going to be greater than or equal to the integral of the log of x dx from 1 to n minus 1. And it's going to be less than the integral of log of x dx from 1 to n. Why? Because this is discrete and the log itself is continuous. All right, so the summation, that's going to be a thing that looks like this, whereas the integral is going to look like that. So since it's monotone increasing, the integral will be a little bigger. And if I chop it one short, I'm guaranteed that the log of I will be one greater. Okay, it'll be going one more box. If you've ever done an integral, my numerical analysis people always had to do some kind of numerical integration and compare it to actual known integrals. And the one common mistake they would make is they go one too many on the endpoint. You have to really cut the numerical at n minus 1 because you're approximating the box between n minus 1 and n. Okay. What's the integral? I'm just going to work on this one. What's the integral of log x dx? This falls into the why you had to take the stuff, okay? Remember this? This is actually, if you pull out your old Calc 1 stuff, this was the actual motivation for learning integration by parts, to do the integral of log of x. And it's so cool. You let u equal log of x. You let v, we don't know, but we know dv is equal to dx. Okay? You make that a different color. Okay. If u is log of x, what's du? Yes, it is cool. I remember I'm a math nerd, so 1 over x. If v is dx, if dv is dx, what is v? X. So by our thing here, this is going to be uv x dx from 1 to n minus the integral of v du. X times 1 over x dx from 1 to n. But that's just the integral of 1 dx. So I get integral of u. Sorry, I wrote dv instead of log x. Okay. So this is going to be n log n minus n log of 0, log of 1, log of 1 is 0, minus, well, n minus 1. Oops, this one will be big O. The same exact argument, this one's going to be omega, which means that our comparison sort, our best case, is theta n log n, which is all we were trying to show. Anything that's a comparison is going to be stuck at n log n. So don't even try to find one that's less. It can't be. By comparison, it can't go down to n or log n. Proof. Done. Come on, that's cool. I forgot the, well, no, because I have limits, so it's okay. But, Ayub, can I point something out? When I took calculus in high school, I never got 100 on this stuff because I always left off the plus C. When I took it in college, I would be stuck at 98 on this stuff because I always forgot the plus C. When I taught calc, I finally got good about the plus C, only because I had people telling me I forgot it. I actually don't need it here in my work because I've got the limits. But yeah, over here, this was a little sloppy. This should have had a plus C on it. I'll give you that. But it does wipe out once the 1 and n go in there. But yes, this is, I didn't get 100 on the trigonometry regions because I didn't put the x and y on the axes of the graph. I also got that points off for that nonsense in, Calc 1, Calc 3, new real analysis, complex analysis. Yeah, I'm careless. I I admit that. It's only when I started teaching that I stopped making those kind of mistakes. I would still sometimes people only gave me 98, but then I argued with them. Um, and I'm an obnoxious student. As an adult, I was an obnoxious student. As a young person, I was yes teacher, yes professor, yes miss whatever. Okay, so we have proven this, and we can pick up with this on Monday. But remember, little o, little omega theta. Okay, a quiz, 10 minutes. We're going to make sure the timer is working okay in Brightspace. I don't want you having time to look the stuff up. I had a lovely surprise from 313. Well, I'll do it at the end of class. Because they did very well on a classwork exercise that I told them it was super important to be honest. Because I was going to decide if I had to do linked lists or not based on what they did on the quiz. And then when I started giving them describing their first project, and I was getting questions that told me, no, yeah, you got 9 out of 10 on the thing I gave you, but you have no idea how to do a linked list. Then I went back and looked and saw all the C's and C minuses taken the second time to get through 212. So you don't really know it. You're only hurting yourself. Ah, yes. Monday at the end of class, multiple guess. Little o, little omega theta. I want to make sure we've got the bright space stuff working okay. It's really March 23rd. Is there anything important? It's the day after my dog's birthday. He'll be 2 on the 22nd. No, the midterm will be the week before. the week of the 16th. Yeah, the quiz is going to be graded. Yeah, I have to know that you know little o, little omega, and theta. Um, but hopefully by having a very strict time limit on it, you won't really have time to go look up the answers. If you try to look up the answers, you'll probably time out. And if you time out, you time out. So don't do that. I need to know that you know the stuff. I don't look at grades as a validation of your life. Well, yeah, when in mine it is, but I just need to know that you're following so far. And none of this is any good if you don't know that n squared is worse than n log n, and that n factorial is a nightmare. Okay, then the whole course is a waste because it doesn't matter if you can give me the right n and n log n and n factorial and whatever if you think that n factorial is an acceptable runtime for anything. It's not. N factorial is going to blow up. Unfortunately, oh, one more thing. You probably got something, an email. The talk today at 12:15 in C205, I think would be interesting for some of you. It's about large language um, models and probability, how things start to build Markov chains. So you're going to hear stuff from 241. You're going to hear stuff that you're interested in, um, AI type stuff. So, and you'll understand it. Maybe some of the math might be a little bit past what you're comfortable with, but you understand it enough. Um, yes, I think the email, the check on, if it's not on the email, check on the CS website, because students are invited to these. And you're, quote, old enough, unquote, to go to them. You know enough computer science to follow. There may be parts that may be a little confusing, only because, they do get into math at some point. There's a reason we make you take the math we make you take. Because if you're doing AI, you need to know something about probability and statistics. And as you can see, if you're doing theory, a little calculus doesn't hurt. Okay. All right. I will see you guys on Monday. And have a good weekend. And remember, Hidden Figures is running. It's on because it's Black History Month, and next in March is Women's History Month, I think. So together, actually, usually Katherine Johnson and them are brought up during Women's History Month every year. So go ahead and watch. It's fun. Okay, guys, take care. Bye. Oh, I put up the recordings.